Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and privilege to be serving you here today, as it is every day here in my virtual classroom. Potentially my last video of the regular school year here, as I'm wrapping up some beats with my integrated Math 1 class as they look at congruency of figures and more importantly, well I don't know if it's more importantly, but more prominently, triangles. Actually, yeah, triangles really are the foundation of all of their polygons, and what we do with congruent triangles, I guess down the line, really do come into play at some point. So this is just that introduction, alongside some things with parallel lines and vertical angles, linear pairs, things like that. So let's jump straight into the action, guys. This is a PDF that I will have down below in the description section, at least at some point, and if I don't, please leave a comment for me, because I upload this several hours later, and it takes a lot of hours to kind of upload and stuff, so sometimes it just gets lost in the shuffle. So, okay, let's just get started with this number one here. I have two pentagons, RSTUV, that are congruent to each other. RSTUV, excuse me, with KLMNO. Let's complete the congruent statements. What is segment TS congruent to? What is angle N congruent to? What is segment LM congruent to? Without the drawings, you can use the concept of corresponding parts of congruent figures being congruent, CPCFC, to understand that this statement reveals everything that you need. No drawings required. RSTUV, letters 1, 2, 3, 4, 5. KLMNO, letters 1, 2, 3, 4, 5. The letter order matters. Not because they're alphabetical, nothing like that. Are they? JK? Yeah, I think so. Not because they're alphabetical, but just where they fit in this thing. TS are letters 3 and 2. If this were drawn, by the way, guys, if this was RSTUV, T and S do need to make a segment with each other, right? TS is a segment. And then KLMNO, kind of the same thing, right? So segment TS, based on that drawing there, is congruent with what segment? Look at the third and second letters in KLMNO, M and L, which would correspond. Those are congruent segments. Angle N, being the fourth letter in KLMNO, is going to be congruent to angle U. And segment LM, being the second and third letters, hey, that's the same thing as segment TS, or in this case, if I want to write it as ST. Look, it doesn't matter which way you write the segments. If I write segment TS or segment ST, it doesn't matter. I prefer, personally, writing it in corresponding order. So, it's the same thing, regardless there. There you go. All right, number two. In this figure over here, if the measure of angle SQT is 5x plus 7 degrees, SQT is right here, that's 5x plus 7. And if the measure of angle RQP right here was 8x minus 11 degrees, then what is x? Well, see, these are two lines. Line SP and line TR intersect at point Q. When you have two lines forming angles that face opposite each other here, these are called vertical angles, and all vertical angles are congruent, something we might talk about a little more on number 4 here. But all vertical angles are congruent, which means these two measures are equal to each other. The measure of angle SQT equals the measure of angle RQP, because once again these are, these are vertical angles. So I'm going to set 5x plus 7 equal to 8x minus 11. And then the rest is algebra, guys. So here we go. If I subtract 5x from both sides, I get 3x. If I add 11 to both sides, I get 18. And then divide both sides by 3, I get x equals 6. So that is what the value of x is, because of the nature of them being vertical angles. If they were a linear pair, then I'd add this with this equal to get 180. But there's not that. However, on number 3, they are asking us to name a linear pair with angle PQT. Now, angle PQT is this guy right here. Here's P. PQT is this angle right there. One of two things can be a linear pair. Remember what a linear pair is: two angles that are adjacent to each other that are supplementary. So example, this angle right here is a linear pair with it because they make this straight angle right here. Write those two. Or this right here would be a linear pair making that straight angle. So you have one of two options. Either angle SQ, it's these two, SQT or RQP, the two that were vertical angles with each other. Either angle SQT or angle RQP, one or the other, more than one answer, not both at the same time. One is a linear pair with PQT at a time. All right, numbers 4 and 5 are all based off this diagram right here, 1, 2, 3, 4, 5, 6, 7, 8. Use the figure to tell what each pair of angles are. So we're asking what kind of angle relationship name they have. Like angles 1 and 2, for example, guys, that is an example of a linear pair right there. Now, linear pairs and vertical angles do not require two lines cut by a transversal. It just requires two lines that intersect each other, and then that's what we have. Angles 1 and 3 are example of vertical angles, as we just saw from the previous bit. Once again, because line M is kind of irrelevant with that. It's just about these two lines that intersect right there. Now we look at something like angles 1 and 5, though. So angles 1 and 5, let's take a look at those ones. Those ones are called corresponding angles. Two lines cut by a transversal, two angles that face the same direction on the same side of the transversal. This, if I call this angle T, or line T, this is the transversal. These are called corresponding angles. And we're going to talk about all these things when we talk about parallel lines, but corresponding angles there. And then angles 1 and 7, if we're looking on the outside here, 1 with 7, these are on opposite sides of the transversal, and these are in the exteriors outside of the two lines here. These are called alternate exterior angles. I'm going to go ahead and abbreviate it as I said it out loud. Hopefully you kind of caught wind of what that said. Alternate exterior angles. All right, 4 and 3. Once again, 4 and 3, another form of a linear pair here. By the way, when I'm marking these with arcs, I'm not necessarily calling them congruent. I am just identifying where they are, what they are. 4 and 8, another set of corresponding angles. Not much diversity in these, guys. Sorry about that. I could have diversity, but I'm just testing to see if you can identify more than one set of each sometimes. 4 and 5 right here. These are on the same side of the transversal, but inside of the angles. These are called same side interior angles. I could have put SSIA. I probably should have. Same side interior angles. My handwriting today is not good. I apologize. It's been a long year. And then angles 4 and 6 are on opposite sides of the transversal, but in the interior. These are called alternate interior angles. This time I'm going to go ahead and abbreviate that. Alternate interior angles. Okay, we use the same 8 angle pairs, I believe, if this was written out the same way. Yeah, it looks like it. And now we're going to be asking, now we're going to be stating that the lines are parallel. Line L is parallel to line M. So what does this cause? Well, I'll let you know whether or not these lines are parallel, linear pairs will still be supplementary and vertical angles will still be congruent because, again, vertical angles and linear pairs have nothing to do with two lines cut by a transversal, just two intersecting lines in general. So wherever you have linear pair of vertical angles, those were going to be congruent or supplementary already anyway. But the corresponding angles, alternate, same side, interior, exterior, etc., things like that, those will be congruent or supplementary now based on the fact that these lines are parallel. Anyway, let's say them out loud first. Which of them are congruent? Vertical angles are congruent. Corresponding angles are congruent. Alternate interior and exterior angles are congruent. When lines are parallel, as a for sure. When lines are parallel, linear pairs are supplementary, even if they're not parallel. Linear pairs are supplementary. Same side interior angles are supplementary. Same side exterior angles are supplementary. So I'm going to go ahead and abbreviate these here. The linear pair angles 1 and 2. All linear pairs are supplementary. That's kind of its definition. So supplementary for angles 1 and 2. Excuse me, angles 1 and 3. The vertical angles right here, those are congruent. All vertical angles are congruent. I'll give the congruent symbol there. I'll just write sup or give the symbol. Angles 1 and 5, corresponding angles. All corresponding angles are congruent when lines are parallel. So congruent there. And 1 and 7, alternate exterior angles are also congruent. Alternate exteriors are congruent. You can kind of just tell when you look at it, hey, obtuse, obtuse. I'm not saying that just because they're obtuse, they're congruent, but if you have a choice of congruent or supplementary, I mean, I've brought that up in other videos. Angles 4 and 3, that was another linear pair there. Those are also supplementary. Another set of corresponding angles will be congruent. Same side interior angles, these two guys, these are supplementary. So again, when I mark them, I'm not marking them congruent. I'm just identifying the two angles as I see them. That is supplementary. And then 4 and 6, the alternate interior angles right here are going to be congruent with each other. right there. So that is your set of those ones there. Now, there's a problem down below which will give that nature, but there are so many different versions you can have. So as long as you know the relationships, you can use them to either set them equal to each other or add them up to 180. Okay, use the figure below. It's kind of to the right, but use the figure to find the values of x and y. Note lines A and B are parallel. And remember, show all work. Okay, so right here, I see a linear pair. It would be super awesome if I said, hey, 4x plus 18 plus 3y plus 26 equals 180. That's a totally okay thing to do. The problem is in this equation, I can't use that to solve for x or y immediately because that's one equation and two variables. There is a way to do this where if I work off of the linear pair here and then the same side interior angles here, I could create what's called a system of equations. And that's something that we did in the past. We solved using substitution or elimination. I'm going to avoid that if I can. I'm going to see if I can just solve for x or y on its own by creating a single equation that just uses x or y, and then I'll go ahead and plug that value in and then find the other. So like I said, it's possible, but it's kind of outside of our wheelhouse for what we've been working on lately. Not that it's not fun. But what I do have, guys, I can make an equation with just x's if I just relate these two angles here. And what are these? These are alternate interior angles. And when lines are parallel, alternate interior angles are congruent. So I can set 4x plus 18 equal to 2x plus 50 because, once again, they are alternate interior angles. And when lines are parallel, those suckers are congruent. Setting them equal. Boom. Subtract 2x from both sides. Subtract 18 from both sides. And then divide both sides by 2. We do get x equals 16. Now I can use that 16 and solve for y either by substituting it in for x here and using the linear pair that adds to 180 as I stated before, or using the same side interior angle pair, substituting it here. I'm only doing the same side interior angle one because we already kind of talked about linear pairs a little more. So I'm going to refer to these two here. Now these are not congruent, at least we can't assume that they are. They're not congruent here, but they do add to 180. So I can now do 3y plus 26 plus 2x plus 50 equals 180. See what I did there? Okay, so 2 times 16 is 32. 26 plus 32 is 58. I don't want to mess this up. 58 plus 50 is 108. So 3y plus 108 equals 180. The rest is algebra. So hopefully you're feeling more about the geometry. You're kind of here for the geometry stuff if I'm going too fast here. Subtract 108 from both sides. 3y equals 72. Divide both sides by 3. You get y equals 24. So there you go. That is x and y. And yeah, guys, systems of equations, if you ever want to come back and see me do a version of systems of equations, I mean, I'd love to go back and see some of those with substitution and elimination. But that's, my goal is not to kind of work that against you. There are other ways. And because the lines were parallel, we could, again, set alternate interior angles congruent and same side interior angles supplementary, adding them to 180. All right, that is the front side of this here little practice test. Now we're going to deal with the triangles and the congruent, when they're congruent, things like that, which ones make them congruent and what you do to prove that. All right, in the figure below, triangle ABC is congruent to triangle DEF. Find the value of each. Show all work for credit. So going back to the idea of corresponding parts here, now we're going to specifically talk about triangles. Corresponding parts of congruent triangles are congruent. ABC is 1, 2, 3. DEF is 1, 2, 3. That means that A corresponds with D. A's angle measure, the measure of angle A equals measure of angle D, and that can help us solve for Y, actually. I don't even know if I want to solve these. In fact, I think I want to solve these in exact reverse order. Segment DE, let's go in reverse. Segment DE, letters 1 and 2. Segment AB, letters 1 and 2. This AB corresponds with DE, and corresponding parts of congruent triangles are congruent. That means that DE's measure is also 64.3. So that's 64.3. Not much to say other than the fact that it's equal to AB as far as lengths go because they correspond. Okay, so also 64.3. Now let's go to Y just because I was talking about measure of angle A. A and D are both each the first letter here, so measure of angle A equals measure of angle D. Therefore, the 65 degrees here also is the same as the 2y minus 3. So to solve for y, I'm going to add 3 to both sides and then divide both sides by 2. And I get, apparently, 34. Not degrees, but it is a part of an angle measure when you substitute it in, which will be in degrees. And the last one, x. See, it looks like to solve for x, I probably needed to get y anyway. So now that I know that y is 34, I can rewrite this expression here as 2x plus 34. And then EF, being the second and third letters, correspond to BC, which is 90.6. So I'm going to have to use some, it's a decimal answer. Apologies there, but 90.6 from that segment BC equals 2x plus 34, which is that segment EF. Subtract 34 from both sides, and I get 2x equals 56.4, I think, and then divide, or excuse me, 0.6, not 0.4, 56.6, and then divide both sides by 2, and you're going to get x equals 28.3. 28.3. Yeah, it looks like I kind of worked backwards there. I at least needed y to get x. There you go. All right, which is not a congruency statement for triangles? Circle all that apply. Well, let's go with the ones that are. Side, side, side works. Side, angle, angle, and angle, angle, side. You could also rewrite angle, angle, side as side, angle, angle. There's a fifth one called HL that I haven't really been getting to with my students. Even though I recorded a video for it, we haven't really touched on it. HL does not appear here. This is really about the ones that do not work. So if it's not here, it doesn't work. I have a video that explains 2 of them that don't work specifically. This one, side, side, angle, or angle, side, side, you know what that spells. That one does not work, so I'm going to circle it, which is not a congruency statement. This is not one. Side, side, angle, or angle, side, side. Again, I do have a video on triangle congruence that does cover that kind of pretty well. It covers it. And angle, angle, angle. This one also does not work. Again, my video does cover that. It's not one of the things here. You do need at least one set of sides to be congruent. In this one, it doesn't work because the sequence, the order that it's in. Angle, side, angle works. That's good. Side, side, side works. Side, angle, side works. And angle, angle, side does work. So all 4 of these do work. These 2 do not. So we circle them as far as going like, nope, I will circle you. So this is what we hunt for, guys. We hunt for any of these sets of sequences as we move forward to number 9. State the theorem or postulate of why the triangles are congruent. Now, currently, we have a set of side, side, which is not enough, right? I need one of these sets here. I either need an angle in between to be congruent, like these 2. There's no reason that I could state that those are congruent right now. I can't think of anything. Or I would need another side, right? And I can get this side here by the reflexive property. All shared sides and triangles here are congruent to each other. So yeah, the third set of sides are congruent here, guys. These 2 triangles, yes, they are congruent by side, 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 side. Reflexive property there. These ones are already all pre-marked, 1 to 1, 1 to 1, 2 to 2. But if you look very closely, guys, this one's scary. You have to be careful. Don't just boom. Because like here, you might say side, angle, side. That's great. But this is not side, angle, side right here. This 2 tick mark thing seems to appear in a non-corresponding part. See, if you wanted it in a corresponding part, it should have been right here. 2 sides in the angle in between. 2 sides in the angle in between. This does not seem to do that. The drawing alone looks a little confusing. When you see that this is congruent to this, but one of these angles looks obtuse, the other looks acute, you can't really go by the drawing itself when it comes to its perceived measure. But what we can go by is a part that should correspond, which is a side next to another side, and the angle in between being congruent. That's not the case over here. So in this one right here, it's not that they're not congruent, but it's that we don't actually have enough information. This one's a not enough info kind of answer, because once again, we don't know. I mean, look, for all we know, maybe this is congruent to this, right? Maybe we have to dig out and deduce that using other means. But if we're not given the info, we're not going to be able to do anything with it. So not enough information here. As it stands, the triangles cannot be proven congruent. This is not a side angle side thing. Remember, this part right here is angle side side. With side angle side, doesn't really work. And this last one over here, I have 2 sets of angles congruent. That makes this an angle bisector. 2 sets of this angle two set congruent right here, two right angles. All right angles are congruent. And then a reflexive property would allow me to put the ones in between congruent here. So these two triangles should also be congruent as well with each other because of angle, side, angle. All right, so there's a set there. This is not numbers 13 through 15. I wanted to take that thing out. But state which triangles are congruent and why. This is just for number 10. So this time, guys, on top of our reasoning for this stuff, we are going to have to make a triangle congruence statement for each, meaning triangle this is congruent to triangle that. Once again, guys, you're going to get a whole lot of, and I apologize for these not being very varied. I really should have gotten some more things with alternate interior angles and angle bisectors and such. But right here, we do have the reflexive property. Let me just mark this up for each. Reflexive property shared side shows these congruent. Hey, the more you learn the reflexive property, better off that I am. Reflexive property here and reflexive property here shows all those things congruent. Parts that you had to mark. Yeah, really should have done more with vertical angles and alternate interior. My bad. But hey, you can still get those things, you know, if you're tested on them and stuff. Make sure that you still know that's going to happen possibly. All right, hey, what could I call this thing? I could call this triangle FGI. How about that? Triangle FGI is indeed congruent to triangle. Well, what corresponds with F? H. What corresponds with G? The other G. And I, the other I. Even though it's unknown what's marked there, this is that's an angle side case, right? The side is outside the congruent angles. These are congruent by angle side. There's more than one way to write this. It depends on how you choose you'd like to write it based on, well, the letters and stuff. And again, these aren't very varied here. But let's keep going. This is a side angle side case here. Side angle side, side angle side. So triangle, I can call this RSU is congruent to triangle. So RSU. I go across the single tick mark, the single arc mark, the double tick mark. Single tick mark, single arc mark, double tick mark. TSU. Triangle TSU by side angle side. Yeah, I really wish there was more diversity in these. My bad. We're gonna see one down here that gets a little more. And then finally part C here with the reflexive property, that does help get angle side angle with angle side angle. Now you got to be careful with this one here because the one arc mark goes with one arc mark over here. That means K corresponds with M. So just be careful when we name these. So let's try triangle K. I'll call it KJM. So K is the single arc mark, J is the unknown, M is the double arc mark in this triangle. On the other triangle down here, M is the single arc mark, L is the unknown, K is the double arc mark. So this is triangle MLK. And that is by what looks like an angle side angle case there. Angle side angle. The side is in between the two sets of congruent angles there in both of these triangles. So those aren't really proofs per se, as in I didn't document them, but I did kind of note reflexive property building it up and got what I wanted. I just need to document more. All right, two more problems. Numbers 11 and 12. Number 11, use the figure to answer, this figure here, to answer what additional information is needed to prove triangle ABE is congruent to triangle CDE using the method described. Okay, so, this can be interesting in a lot of different ways because when I had done this with my students, I had stated that this is the only amount of truths that you could actually do. But right here, I see vertical angles being congruent. If you guys actually learn enough stuff, you'll actually learn that these lines are parallel because these alternate interior angles are congruent. That creates alternate interior angles here to be congruent. It's kind of a weird thing. So there are other truths that we could pull out if we knew the information about them. Let's assume nothing else was actually known to be true and said what else would have to be true for us to get one of these. Meaning I got angle side, and what if I need angle side angle? If I want angle side angle here to make these two triangles congruent, I need angle side angle here. Now there is a way to show these are congruent. There is a way, but let's name what these angles are. Let's not just mark it up. I would need angle, I can call this BEA, angle BEA, and I can't just call it angle E, right? I got to use three letters here. Angle BEA is congruent to angle, I can call this DEC right here, angle DEC. That would give us an angle side angle version of this thing here. If I wanted to do angle side, now this time the side has to be outside the congruent angles, which means we're talking about this one congruent with this one here. Once again, something that actually could have been proven to be congruent if you knew what you were doing with it. I don't think you guys know at this point. But that's angle A and angle C. And yes, I can just give a single letter for these ones because I'm not going to confuse what that angle is just by calling this one A. Whereas if I call this E, a lot of confusion. Last one, side angle side. So for this one, the congruent angle needs to be in between, and I assume they're talking about the right angles, which are already congruent. That means these two sides would have to be congruent. And I'll tell you what, right now, there is no reason for me to state and know that these sides would ever have been congruent without me just saying that, hey, if these were congruent, then these two triangles would be things. So actually, here, let me put the if. If only they were. If only they were. These two kind of are, but if only this one was. Segment AB is congruent to segment, how does that correspond? CD? Segment CD, like that. If only, right? Okay, last one here, and I'm going to build the whole proof with you. Now keep in mind, as I've done a lot of proofs with my students here, there are so many different proofs to do. I just had so little space to fit on this thing, and I just wanted to just cover one, and let's just talk about it. All right. Let's give a proof. Let's prove that these two triangles LMN and PON are congruent to each other, understanding the fact that LP and MO bisect each other. Now, these are segments that bisect each other. Segment bisectors intersect at each other's midpoints. If they bisect each other, that means N is the midpoint of these two things. Okay, that's only important to kind of state how these things work. But anyway, let's start with the given. Segment LP and MO, or segments LP and MO, bisect each other. Whoa. Each other. That's given. I'll be honest, I think I need more than 4 steps. I think I need at least 5 steps for this thing. But it's given that they bisect each other. I could write 2 things in 1 step if you truly want me to. That's totally fine. We'll save it as 4 steps. If they bisect each other, see, it's not just LP's bisecting MO. MO's also bisecting LP. That means MO is dividing LP into 2 congruent parts like that. That means that segment LN and segment PN are congruent to each other, because that is what segment bisectors do. That's the defection. That is the definition of a segment bisector. But wait, there's more. MO doesn't just bisect LP. LP also bisects MO. That makes MN and ON also congruent to each other. So I'll just put this on this one if that's okay. So I'm going to also mention that segment MN is congruent to, again, my handwriting, I don't know what happened here today, is congruent to segment ON. So I'm just putting them on the same line because they kind of come up with the same thing. After all, these were both on the same line, bisecting each other, and here's what it caused to happen. Now I need to find one other set. Can I somehow get these sets of sides here congruent? No, there's nothing really I can work on with that. I can get these 2 angles in between congruent, though. These are vertical angles here, right? I can say this angle is congruent to this angle because all vertical angles theorem. So I can say angle, and I got to give the 3-letter thing like MNL. Angle MNL is congruent to angle, how about ONP? ONP, because the vertical angles theorem. I do have a side angle side case here for these 2 triangles being congruent. Triangle LMN is now shown to be congruent to triangle PON here because I got a side angle side right there. So last statement is the proving statement. Triangle LMN is congruent to triangle PON by side angle side congruence theorem. And that's it. All right, so that'll be it for this stuff here. There are obviously other things that could come into play if we use some more things on CPCFC. We even did that with some proofs. Things more with corresponding angles, setting them congruent. I don't know, some other things here and there, but that is the basic crux of these things, guys. Really working in the triangles at the end, working on the reflexive property of vertical angles. No alternate interior angles really popped up in the triangles, but hey, they could. So I kind of made mention of that as well. But anyway, that'll do it for me, guys. I got under a half hour. Awesome. Thank you so much, and take care.